sure what it is, but it's cute. All right, the next spotlight is DeepRL in a handful of trials using probabilistic dynamics models, presented by Kirtland Chua.
Hi, everyone. I'm Kirtland, and I'll be presenting deep reinforcement learning in a handful of trials using probabilistic dynamics models. This has been joint work with Roberto Calandra, Rowan McAllister, and Professor Sergey Levin. Deep reinforcement learning has been successfully applied to many domains, but many current methods often require a significant amount of data to learn tasks well. And so this is an issue in most real-world scenarios because oftentimes we are constrained by resources as well as factors such as wear and tear. And so how can we speed this up? So one prior approach is something called model-based reinforcement learning, where we have the agent learn a predictive model of the dynamics of the world, which it can then use to plan its own actions. And the key idea here is that by leveraging more supervision from our interactions with the environment, we hope that the agent would learn faster. But how well does this actually work? So here we have a model-based method in orange, a model-free method in purple, and the y-axis represents the performance on the half-cheetah task. And so we can see that the model-based method indeed learns quickly compared to the model-free method. However, in the long run, the model-free method eventually outperforms the model-based method, which plateaus earlier on. And so how can we have methods that are able to match the asymptotic performance of model-free methods while having the data efficiency of model-based methods? Let's look at what prior methods have done. So in prior methods, we have a neural network which takes in the current state in action and gives a point prediction of the next state. And so to illustrate the issue, let's consider a toy function and assume that we have samples as well as a neural network that approximates using these samples. So we can see that the neural network is accurate close to the training data and is inaccurate far from training data. And the issue here is that the agent does not know where these regions are, and in the reinforcement learning setting, the agent will have to constantly see states it hasn't seen before in the process of learning. So we modified the model so that it can incorporate two kinds of uncertainty. So the first kind is noise in the data, which we modeled by having the neural network output a distribution over the next state. This allows the agent to plan even in the presence of noise in the environment. The second kind of uncertainty is uncertainty in the model itself, which we captured by having an ensemble of neural network models. And so we can see that the models generally agree close to the training points, while they disagree far away from training data. And so we can take this disagreement as a measure of the uncertainty in the model itself. But how do we actually incorporate these estimates into planning? So the method we use is something called trajectory sampling. And the idea is that given that the agent is currently in a particular state, what we can do is, given an action sequence, we can simply have each network in the ensemble give its own prediction of the resulting trajectory. And so, for example, in this case, we have a particular action, so each network gives a distribution over the next state. And so we sample from this distribution, and we perform this prediction recursively. So we get new distributions, we sample again, and then we sample once more. And this then gives us a bunch of samples of the possible trajectories as predicted by the model. And so how well does our method perform? So here we have our method in blue, the state-of-the-art and model-free methods in brown, and a prior model-based method in orange. And so we can see that our method is able to achieve the asymptotic performance of the model-free algorithm while requiring significantly less data. In fact, we are able to achieve a running gait with the half-cheetah in under 10 minutes of interaction time with the environment, while the model-free algorithm requires several times more data to achieve the same level of performance. And so we called our algorithm PETS, which stands for Probabilistic Ensembles with Trajectory Sampling. If you're interested in more details and more experiments, please feel free to check out our paper, as well as our as well as our poster at the poster session. Our poster number is number 165. Additionally, we've provided code for all of our experiments. Thank you.